The talk today, it's about energy and about, in particular, its science and communication. Who are we? She already said a little bit. And I'd like to spend a second about this because it's a pretty strange mixture. Alessandra, she's a journalist. She writes on a number of newspapers and journals. She produces also cartoons for kids. In particular, she's a specialist in science journalism. And we met for this reason because besides boarding the airplane in the normal way with respect to her, I'm a scientist, so I'm teaching physics at Padua University, and I'm responsible for an experiment which deals with energy, in particular with thermonuclear fusion. We met for professional reason, and we thought it would have been nice and interesting to exchange experience on the way we both communicate science. And therefore, this lecture and a number of initiatives that we are doing over the months, it's on this topic. Our talk today follows 3 steps. There will be an introduction, then a first part that it's the science of energy, that will be basically on me, and the final third part will be about communicating energy, that will be for Alessandra. Let's start with the very first part, and in order to do that, while you're reading this, I'm an experimental physicist, so I brought with me a little bit of equipment. That's just a bulb, standard 100 watt light. It's old-fashioned, it's not low consumption. But why I put it there? Because a person, it's normally, you can consider each of us about a 100 watt engine, assuming that we can work on a continuous basis. So if we climb the stairs or we climb a mountain, we walk, in Venice, we roughly speaking, of course it depends on your level of training, but it depends, you are basically 100 watt engine. Well, therefore that lamp, that light, it's 100 watt, which means that if you leave it open, you need one person cycling, for example, 24 hours a day, just for that specific lamp. Or if you want to be nice, 3 persons working on 8-hour shift, which is, it's a lot. Just remind that an average European family household has about 400 watts of steady consumption at home, which means that you need 4 people working for each of our houses, cycling 24 hours a day. You might think that this is a lot, and it is in fact, but just to give you the feeling, if I let that lamp on for a day, this is going to cost us, maybe 30 cents, which really give you a sort of disproportion between the actual cost, what we really pay for energy, and what really energy is, the value of energy for our society, and how precious it is, which is something that, after since about a century and a half, we sort of lost this comparison because, starting the usage of fossil fuels, we sort of miss the connection to human work of energy, but certainly it's something that you have to take into account. And also, another important point is that you may really solve many shortages as long as you have usable energy available. That's, for example, the largest plant for desalination. It's in the United Arab Emirates. It has been inaugurated, I think, a few months ago. It can provide about 630 million liters of water per day. Of course, it needs a big battery, a lot of energy. But just to say that if you don't have fresh water, you can get it from the sea if you have energy. The only thing you cannot replace, you cannot substitute is energy itself. If you have a shortage of energy, then you're really in trouble. That's why energy is so crucial. It's so central to a number of parts of our life. For energy, you do wars. Energy has a big impact on the environment. We know about that. That's Beijing. in a standard day. Energy is on the press, and Alessandra will talk about this. Energy had a big role. For example, that's two snapshots taken from the last presidential campaign in the United States, and you see that both candidates, really hit this topic of energy. Energy has to do with economy. If you want to get these days the metric of reputation, the modern metric of reputation, just Google something. And if you Google energy, you will find around about 1,600,000,000 hits, which is far above politics, for example, more or less the same number of education. It's 4 times soccer, which for this country is kind of strange, and it's even larger than the stock market. So it's really something, and it's a simple indicator, but it tells you, I would say, a lot about this. Let's go back a little bit on how this lecture of today in particular started, and why the idea, with Ignazio, I know Ignazio since a long time, and we've been chatting about this experience and a course that we'll do for scholars in political science in September. And so this idea came, and that's why we are here today. And in fact, exchanging a few views with him and with other friends in Padua, I just try to get something like all the economy in one page. And for example, I noticed that what Ignazio teach has a lot, of course, of words and terms concerning energy. I was pointed to, of course, I'm not an economist myself, but to one of a famous economist of the 60s, I think, that used the concept of entropy, of laws of thermodynamics within his economic theories, just to say that, even for, not only for the large society, but also when you go into economical and political science disciplines, energy is playing a key role. I'm finishing this first part, just remembering that that's a sort of breaking news. It's from today. Today, the head of governments of the European Union are meeting in Brussels for a summit which is dedicated to energy and taxation. I took the official press release from the European Commission, and there is this nice program that allows you to produce a cloud of the words, and the size of the words is proportional to the number of times that you find that word in the document. And in fact, you can see that words like energy, efficiency, growth are central, for example, to the meeting of the European ministers today. And in fact, if you read the letter of invitation of the President of the EU Council today, they will try to answer to a number of questions: further increase energy efficiency, to further develop indigenous resources, and to achieve a more predictable energy policy. It's interesting that, again, to show the contact between science and politics, that all these words are something that I use, for example, in a science course. But if you listen, if you try to understand behind the scene, this means interconnection of the German network, shale gas in Europe, yes or not, a number of things. From all this, we said, okay, let's try to see whether we can put together a lecture where we try to give the basis of the energy science and of energy communication.
I'm a different side from scientists. I work in communication, so I will talk with you about another way to look at science, and in this particular case, about energy. Energy is just to say energy matters for us. It's really something very important. It's really something that we use in every context, in every moment of our lives. It's a key factor of modern world. Actually, has always been something really precious and really important since the discovery of fire, if you think about it. So everything relies on energy, from transport to surgery to communication to factories. Everything is based on energy nowadays. This is the world energy consumption in the last 2 centuries, more or less. And you can see how it raised. It's almost vertical now, except for biofuels. That means more or less wood. This is something we always used. Let's have a look at nuclear. Nuclear is really, you know, kind of very, very vertical. It's exajoules per year, so it's really a big amount. But there's also a very deep correlation between energy and human development. So this is an index that United Nations developed to study, you know, how life expectancy, education, and income are related to energy use. So you can see how the biggest energy consumers are also the places or countries where this HDI index is higher. So the more energy you consume, the more your life is good. It's not so, you know, it's not so simple. It's not so easy to say it, but it's evident. For what can also be of some interest for you, Piero tried to Google energy, the word energy. I tried with work, so I Googled energy law firm just to show that this means 214 millions of results. So it's just in in law firms. So you can imagine how many works are waiting for you if you are interested in energy. And there is also this is a federal office of the United Nations government that is specialized in plain language, in explaining government to how to communicate better its politics. This is because despite this widespread scientific illiteracy, the public is confronting many important science-based choices. And the first one is, I think the most important, about 50% of the major bills that come before Congress contain now a major scientific or technological component. So, and you know, politics are really not prepared to this. And also juries are evaluating more and more technical evidences. And we also face every day more scientific topics in our lives. And we take important medical decisions for ourselves. And more, this is a recent National Science Foundation study that shows that something really incredible, if you think about it, that fewer than 50% of adults understand that the Earth orbits the Sun. It means that the other 50% thinks we maybe, I don't know, orbit the Moon. I don't know. But it's really incredible because many, many centuries passed from Galileo to today. And only 21% can define DNA, and only 9% know what a molecule is, and so on. That means that really science needs to be communicated, needs to be understood. I mean, you can live without knowing if Earth orbits the Sun, but I mean, I think you miss something if you don't know it. And you miss something in your choices, in your personal choices. But is it true that science is really difficult to be communicated? This is Professor Martin Blackboard. So actually, you really need to consider your target. So this was target to a physics class. So students were, prepared. I don't think you or me, we can understand anything here. Can you? So before talking about how to communicate energy, let's ask what is energy. So what are we talking about, Piero?
The second part of the talk. Why we took energy, by the way, because as Alessandra pointed out, the problem that, for example, the United States government identified about scientific illiteracy, deals with science in general. Of course, science is a big, big field. We, for the reason I mentioned before and with the connection with the VIU and for a number of reasons, and also for the fact that we have an hour today, we decided to concentrate on a particular topic, which is energy, which is a subsection of science. But of course, it's a pretty big, pretty big area. And the sort of challenge that we try to address, of course, only a little bit in this talk, but more generally in the activity we try to do together, it's to see where there is something in between the language of physicists. These are two wave equations, for physicists, they're rather simple, straightforward. They describe the behavior of the electric and magnetic fields in a wave that would probably tell you almost nothing, but this is at the basis of the use of the, of the explanation of how a cell phone works, our radio works, how light is transmitted from the sun to us. So that's, our microwave oven works. But of course, if we address the point in this with this language, only a reduced number of the audience can follow it. On the other side, you might stay on the, at the other extreme, being just plain users, either of the cell phone or the microwaves, or even to some extent worse. So this is not a joke. I just found a website of a group which is very active in trying to demonstrate how bad the microwave ovens are. And it's interesting enough, this group, it's using a number of scientific terms, maybe mixing the test that the Russians did with the radar on people in the 40s during the war and the actual microwave we have in our kitchens. But, just to say that in between a full scientific illiteracy and a specialized language, there might be something. And that's why what I'm trying to address in the next 20 minutes. As I said, I try to summarize it will be a big challenge in 25 minutes, the whole science of energy. So it's going to be difficult, even because, Richard Feynman, which is a physicist much more famous than me, it's a Nobel Prize for Physics in 1962. One of his most famous quotations is that it's important to realize that in physics today, we have no knowledge of what energy is. Of course, it was sort of, on the extreme side, but to some extent, it's somewhat true. Energy is not a simple concept to explain, and even economists, say that the concept of entropy, for example, is so involved that even physicists may go wrong with it. So let's try to address this point as good as we can. First of all, energy, it's a single physical quantity. That's important. We have only one quantity, which is called energy, but it may come in various forms. Some of them are very familiar with us: thermal energy, heat, for example. Electromagnetic energy, maybe it's a little bit less familiar, but we use it every day. Each of us has in his pocket probably a generator of electromagnetic energy, which is a cell phone. Of course, nuclear energy is on the press a lot. Chemical energy, it's kind of maybe hidden behind this name. It's something which is very, very much familiar to us, which is just gas combustion, any kind of combustion of a fuel. Release chemical energy. So energy comes in various forms. If you just look to this projector that is just producing this image on the wall, it's a very neat example on how we can transform energy from one form to the other. In fact, that's an interesting point. That's the number one point I like to make. And in fact, energy is not going. We do not consume energy. We just use it or we transform. For example, you do have as an input electric energy in this projector. Of course, yes, as an output, this energy goes into electromagnetic field energy, which is the light, which hits the wall. But of course, if you put your hand up there, you will feel warm. So you do have also as an output thermal energy, and to some extent a little bit, but that's energy too, sound. Sound is also a way to disperse, to transmit energy, and there will be probably some fan coil that cool this stuff that is going to release a little bit of energy. Net balance, zero. Energy is conserved. And this is what physicists call, by the way, the first law of thermodynamics. Energy is conserved. But the different form of energy do not have the same quality. That's the second law of thermodynamics, and I'm going to go into that in a minute. As I said, energy is never consumed. It is transformed from oil. You know, you can produce electricity, you deliver it, you can cook food, you eat food, you transform it into your own energy, you run, and eventually you dissipate as heat. Almost unavoidably, each kind of transformation of energy ends up into heat. Excuse me. Heat is the final result of all energy transformation. Of course, energy transformation are key because in order to be used, you cannot drink a glass of petrol and try to get the same energy that you would get during the whole cycle. This already sort of give you the feeling that the topic is going to be really very broad. Let's try to address it on a subset. So not only from science I picked a subset which is energy, but from energy I pick a case which is the case of electric energy because it's probably the one that all of us use more frequently, are more familiar with. Well, electric energy, it's interesting to know that I would say maybe 90% of the electric energy that we use today comes from movement, from what physicists call kinetic energy, but which is energy related to movement. And this gentleman in 1831, Mr. Faraday, showed that just by moving a copper disc into a magnetic field, the one that you can produce with a magnet, you can produce electric energy. There is a very nice anecdote because he was visited by the finance minister of Britain, who was very interested, of course, about this new invention. And this minister asked Faraday, "What are you going to do with this?" And he said, "Well, I have no idea yet, but certainly one day, sir, you may tax it." And in fact, he was pretty right about this. Interesting enough, the idea of Faraday came across over the century, and it's now the way we produce electric energy. Probably if you run a bike, well, nowadays you have just a light with batteries, but in the old-fashioned bikes you have what we call a dynamo, which is indeed an alternator, which basically what it does, it transforms movement energy into electric energy. Movement, we said. Movement is basically a part of mechanical energy. And mechanical energy, as I said, it's movement. Let's take the example of the skier. So when you have a body which is moving, it has an energy. But it's also potential energy. How you gain this kinetic energy? That's a sort of more theoretical concept, but it's probably easy to visualize if you think that you are on top of a hill. On the top of the hill, your kinetic energy, your movement energy is very small, but where you go downhill and you go down to the valley, you transfer what you call this potential energy, your available energy, into movement energy. And when you are down here, your budget of potential energy is gone. It's gone where? Into kinetic energy. And in fact, in order to gain again your potential energy, you need to pay a price. For example, take a lift, cable car that brings you up to the top of the hill. Interesting enough, the sum of movement energy and potential energy, it's again constant. That's why I was saying that energy conservation is one of the key factors for physicists. You can transform one in the other. For example, on top of the hill, all your energy is potential, zero kinetic energy. You go down, you see the sum is 50, 20, 30, 35, 15. You almost lost all your potential energy and you get kinetic energy. You make a jump, you slow down, your movement energy is smaller, but your potential energies get higher. And eventually at the end, you're all into kinetic energy and nothing in potential energy. All right, but we said we wanted to make the electric case. What has this to do with electricity? That, as I said, a number of ways, almost 90%, I would say, of the electrical power produced today comes from movement. There are very simple and direct examples that you can visualize, thinking to dams, for example, hydroelectric power. station, you do have, what is the movement? The mass, the body, the movement is the water. It falls down through this duct, and this is your bicycle dynamo, basically, it's the alternator. Here is the generator, and you make energy out of this jump of water from a higher level to a lower level. Wind. Wind is also wind power. It's also transforming wind movement energy into electrical power. Tidal electricity generation. In Normandy, for example, there are a number in places where you do have big tidal jumps. You do have generation of electricity due to the fact that the tidal wave enters the harbor, and then when it goes back, and again you can produce electricity. But this, I should say, it's just a subset of the way with movement you produce electricity. Most of the electricity is produced indirectly, well, directly through movement, but movement is produced indirectly. In which way? Heat. Heat, thermal energy, as we call it, it's very familiar to us. If you just light a match, if you are in front of a fire, you get heat or thermal energy. The thermoelectric power plants work exactly in this way. You heat water. That's interesting enough. It's just like you're cooking when you're cooking with your pressurized pan at home. And basically, the idea, again, is the same. It's very simple. It's the same idea of the bicycle. You do have your turbine and the alternator. Here, what is placing this generator into movement? Well, it's just high pressure vapor. If you know that when you end up cooking with one of these cookers, vapor cookers, you open the valve, and a jet of vapors comes out at high pressure, and it has some movement. It brings some movement into that. Imagine to do it on a huge scale. You burn fuel like coal, gas, oil. You boil water, you produce high pressure, like in your kitchen, and then this high pressure vapor enters the turbines, put the turbines into movement, and eventually you make electric energy. Once again, high pressure steam movement is transformed into electricity. And look how many transformations you have here. Fuel, movement, electricity. So chemical energy, movement, and electricity. By the way, if you just look more or less in that direction, you have pretty huge, it's probably the fourth or the fifth in the country, power station, which is here in Fusina, which burns gas and coal. Well, what's the problem of burning? Because it seems easy from the physicist's point of view, but what's the problem of burning fossil fuel? And Alessandra will come back on this. Fossil fuels derive from the sun energy. As you know, it's a pretty long story, but it starts 100 millions of years ago. The sun was letting the trees grow, then they fall, and then they were transformed by the heat and pressure, first as lignite and then coal, and that's what we are using today. So we basically are using sun energy, but which has been stored for us millions and millions of years ago. But how we use it? We burn it. What's the problem of burning? That's a standard, don't be too scared from this. That's a chemical reaction. It's the chemical reaction of burning. Methane, oxygen, you produce CO2 and water. The real problem is that you transfer chemical energy of the fuel into heat, but you produce CO2. That's something that you really don't want. As you know, it's what is considered to be one of the major responsible for the greenhouse effect. And that's a graph that show you the average production in tons of equivalent carbon emission per capita in 2008. And we are doing not too bad, but United States are really doing good. Well, of course, it's a bit ironic this in terms of production. In this, and now I think I'll try to finish in 5 minutes, so to leave Alessandra time enough for her part. I should say that one of the issues, of course, of burning fossil fuels is that, first of all, as we said, there is this problem of combustion and therefore production of CO2 in this transformation, again, chemical energy into heat. But remember that energy is also key for transport. One of the most important use of energy today is transport. Let's think a little bit how your car engine works. You get another transformation, chemical energy, which is into fuel. You burn the fuel, petrol in this case. You make mechanical energy in your engine. And this mechanical energy through the shaft is transmitted to kinetic energy, to movement, once again. But a lot is dispersed. Actually, the efficiency of a car engine is pretty low. It's the order of 30–40%. So a number of a fraction of energy is dispersed. But why it's so important to use petrol? Why it's so useful to use petrol? Because of a concept which is called energy density. And it's one of the reasons why oil is so precious. If you took petrol, for example, with 52 liters, which means around 60 kilograms of fuel and tank, you can run probably, with a good car, 800 kilometers. If you want to use the same amount, if you want to run the same amount of kilometers with hydrogen, you need to have a tank which has a mass of 400 kilograms, because hydrogen under high pressure needs a big tank. And if you want to use batteries, that's why one of the problems why electric cars still have problem is that the weight is going to increase in order to get this range that petrol gives you. It's really going to increase a lot. So the energy density of petrol, of fuel, of oil, it's really very high. And that's why one of the origin of the metaphor that Alessandra will talk you about. Do we have alternatives to heat water and produce electricity? Yes, of course there is sun. You can concentrate sun energy with mirrors and heat directly water. That's a big power plant that is in Seville, near Seville in Spain. Or you can rely, that's my last topic, on nuclear energy. Nuclear energy comes from the structure of the matter. If you took that table, you enlarge, you will see that it's made by atoms. Atoms are really very tiny, about 1 billionth of a meter, so you can see by eye. But if you look into the details of an atom, you will see that it has a nucleus and electrons going around. Well, it's interesting that when you use chemical energy, you work at this scale. You rearrange atoms into different molecules. You go from methane, oxygen, to water and CO2. So you work on this scale. When you use nuclear energy, then you go on the nucleus scale. Of course, this figure is completely out of scale. There is a fraction of a million between the size of a nucleus and the size of the atom. So just to give you an idea. But because of the large amount of energy which is stored into the nucleus, you can get a lot of energy out of fission, which is based on splitting heavy nuclei into lighter nuclei, and that's the way the present power plant works, or fusion, which is when you put together two light nuclei in a heavier one. Just a quick reminder this is fission. Fission, it's basically the plants like Fukushima or the big power plant working nowadays. It involves heavy nuclei, like for example uranium. You break it, and you get lighter nuclei and energy. What's the big problem of fission is that its products are radioactive. And then the big problem of fission is that you have to store the waste for a long, long time. Fusion, the other extreme, which is, I've spent a couple of minutes on this because it's a bit self-advertising and working on this field. Fusion is the process which heats the sun. You do have two sort of, I would say, isotopes. It's a technical term, but it's basically cousins of hydrogen that merge together. You produce helium, that's the gas that you use to inflate balloons, for example, and neutrons. And out of this process, you get really a huge amount of energy. Our universe here, our life on the Earth, exists. We exist because of fusion, because the sun burns a lot of hydrogen every second just to produce the heat that is serving life to our planet. We are trying to reproduce this, and in fact Italy is at the leading edge of fusion research. That's an interesting point. And by the way, if some of you are interested, our lab, it's just 40 kilometers from here in Padua. It's open to the public, and we do have this experiment, which is called RFX, where we try to reproduce the process that is powering the sun. It's a big challenge, and we try to, we try to achieve this. And again, what's the big advantage of fusion? I'm sorry for this. This is Finnish. I just steal this slide by a colleague, but it's nice, also keep it in Finnish. But anyway, it just tells you that in order to run a 1 gigawatt megawatt electric power station like the one that we have here in Fusina, just to give you an idea, you will need for 1 year, you will need something like a train full of carbon, or just a number of if you take wood, how to call it, trees, a number of trees that lined up would cover the whole Finland, or just a couple of trucks of uranium, or a small car of hydrogen, in order to make if we were able to run fusion. Well, energy is concerned, problem solved? Not really, unfortunately, and it's not really, because every time you transform energy, you lose quality, and I come to my end. This is a car, and when you brake your car, look at this circle here. This is very hot. These are the brakes. You're transforming movement energy into the car into heat. This heat, in particular heat at low temperature, is unfortunately not useful to produce work. And this is not something that we decide, is the nature that decides for us, because it's the second law of thermodynamics. And in fact, there is a concept which is called entropy that measures the energy dispersal. And unfortunately, energy is conserved, but when we use energy, we convert a given amount of it with low entropy into the same amount with higher entropy. And unfortunately, energy is still there, but cannot be reused. Only low entropy energy is useful. So more than energy problem, probably the real problem is entropy for environment and for the sustainability of our economy, because you all know that getting 1 kilowatt hour out of the plug is very much different from getting the same amount of energy stored into the water. Good, and I think that with this slide, I see that I'm a bit over my time, so I conclude my part here. We can leave it for the discussion. I had a little bit more about energy storage, but I don't want really to use Alessandra's time. So I stop here, and with this picture that was pretty interesting for me to visualize the concept of entropy. You start every time you start with an energy like petrol, for example, which is very dense, very concentrated, but unfortunately nature brings you in a situation where this energy is much more dispersed and unfortunately much more unusable.
Welcome in the third part of our lesson, communication energy. So who is this for? I think this is for you now, but who else? And what is this? What are we talking about, and how do we do it? This is the way we are going to go together. Who cares about it? I mean, we said many people, but who? Economy is really interested in energy, as we have seen. Population, everybody is interested. Health, we need energy for our health, and also environment. These are really the four sectors that are mainly involved, mainly interested in energy. We already know this is a really important topic. At the point we even have a festival that now tries to, put in communication people with energy. So to explain, l'energia spiegata means, energy explained to people. It's a energy festival. It's now at its third edition. energy has an internal push, to communication. First of all, because we all receive energy bills, so energy talk with us, not in a very nice way, but anyway. But we also, I'm sorry?
It's like the taxpayer.
Yeah, definitely. And also, because of these symbols, I think everybody knows what does they mean. For household appliances, they show how our household appliance is efficient. And energy also communicates by media and also using advertisement. This is a campaign for safe use of nuclear. It was an Italian campaign in, I think, 1994, 5, something like this. But how does energy communicate? So energy really uses special tools to talk with us. 3 in special. Lexicon, so special words. Metaphors, special ways to combine words to put more meanings, to give more meanings to people. And sensationalism. And we will see how important is this third part. Let's go a bit deeper. Lexicon. Science is based on the perfect adherence of the words to their meanings. So we tried a really short experiment with Piero. We choose a word that is radiation. I went really very fast. I'd like to ask you, what do you think about it if I say radiation? What's the first thing you think about?
Something good or bad?
Something bad.
Yeah.
And something more?
X-rays. X-rays.
Okay. And then? Radioactivity.
I think of the sun.
Sun.
Good.
Perfect. Okay, so we will see how we define the same word, being a scientist and being a communicator.
Radiation, it's one of these kind of words that is really a bad luck, because like nuclear, for example, it's unavoidably they are associated to negative meanings. For example, take radiation. Radiation, it's the way that our GPS work, because the electromagnetic radiation, which makes up the signal that comes from the satellite and use from our GPS to locate ourselves and to show us the road, is based on radiation. We use radiation every day in our kitchen, but also with our cell phone. Radiation, somebody said the sun, and indeed radiation has it's a beautiful example, has some beautiful, gives origin to some beautiful natural shows like aurora, for example, in the northern countries, which, by the way, it's again responsibility of the sun, because this is a kind of radiation, or particles in particular, that comes from the sun. They travel a long way from the sun up to the Earth, and they find the Earth magnetic field, and they are diverted into the North Pole, because the Earth magnetic field and the way the Earth is made ends up into the North Pole. And hitting the atmosphere, you get this beautiful light. And you see also only north. By the way, this radiation, this one, which we luckily observe only for fun, it could be really deadly if we had no magnetic field around us. You know that if you take the Earth is like a big magnet, it's like having a big magnet inside, and this magnet is protecting us from this flow of particles from the sun. If there was not this magnet, we would be lost. There would be no life on Earth. And as somebody said, X-ray, these two gentlemen, Alan Cormack and Godfrey Hounsfield, are two physicists, but they won in 1979 the Nobel Prize for Medicine for the discovery, invention, I should say, of the tomography, the CAT scanning, which every day it's it's saving thousands of lives in hospitals because it's one of the tools that doctors use. Of course, radiation is also the one that comes out from the power plants when you have an accident. Fukushima, it's an example of how radiation could also have a negative meaning. But just to say that these terms has a very precise technical meaning, and we should be aware of this, that there are the bad meanings, but there are also the good or the neutral meanings of that. And unfortunately, a number of times, the press it's just focusing our attention on the bad meanings.
Well, this is how science works. They really like to explain. They really like to be clear. They really like, that everybody can understand. Okay, how do we work? We really like, to study topics we don't know, so we collect meanings, and we can see, propagation of hazardous substances, nuclear waste, also energy transport in space, and microwave oven. But what we do prefer, like as journalists, is to make big things, big titles. So radiation is nuclear waste, is something bad, more or less. It's propagation of hazardous substances. We don't really use radiation for microwave oven very often in our papers. We prefer to use metaphors. That means we sometimes add meanings to other meanings. Everybody, I think, knows what a metaphor is, but I looked in Wikipedia just to be sure that it's a figure of speech that describes a subject by asserting that it is, the same as another, otherwise unrelated. For example, table leg. For example, black hole, or dark matter, or greenhouse effect. Of course, a black hole is not a hole in the sky, but it gives a really strong idea, a strong concept you can think about. Why do we use metaphors? We will see in a second. For example, I chose two metaphors to show you today. The first one is about oil, and it shows why we consider oil a precious good. And I took this from Alan Heger, I think it's the right pronunciation, but I'm not sure at all, that said, burning oil to produce energy is like burning old furniture to keep warm. You can see, what a stupid thing is. What extra meaning brings you this image? Please help me. Any extra meaning? Would you ever use your old furniture to keep warm? I don't think so. I mean, you can really do many useful things with your old furniture. You can maybe sell it if you really need to keep warm, but you're not going to burn it, for sure. What does it mean, going back to oil? That oil is really precious good, and we are burning a lot. But we also use oil, for example, to do other things. We need oil to do plastical things. And once we will burn all the oil we have, we are not able to do plastic anymore. So metaphor has an evocative power. I can say some of you will remember this, this old furniture burning more than other slides. And it's brief. It's something really shocking, no? It's really that brings meanings, sometimes misleading also. I apologize for that. But it's also of easy memorization. So it's really important to communicate science, because science is made of difficult concepts. the thing is, it's not simple to communicate, for example, nuclear fusion. Professor Martin explained us before how nuclear fusion works. I don't know how many of you can, repeat what does he said. I mean, he gave you a general idea, but let's see if it's clear, maybe. I choose another Nobel Prize, for physics, is Pierre-Gilles Desjardins, that said, we say that we will put the sun into a box. The idea is pretty, actually it is. The problem is we don't know how to make the box. Let's see. Put the sun into a box. There's something really difficult. You imagine put this really big and very, heat object inside a carton box. There's something really, really difficult to do with this. And it really explains very, very well what is the problem we are facing now in nuclear fusion. How to, to put the sun inside something. How to collect this big, big energy we can produce. This is the biggest problem we are facing now. I think so, hope so, more or less. But also, another metaphor is you can put the sun into a bottle, because previous experiments tried to put the sun into a structure that have a bottle form. The problem is the same, of course, because the sun can melt glass. Now we are trying with electromagnetic fields, I think. Yes. And with something that is not, made of material, because nothing can contain a sun or an energy similar to the sun. Let's go to the third part. I said we, as a journalist, we really like sensationalism to communicate science. That means that to write a paper, we consider some criteria, some newsworthiness criteria, because we can't just, write about nuclear fusion. We, wake up and decide, okay, I'm going to write a paper about nuclear fusion. But we need some criteria related to news. Something new happened, maybe. Maybe Professor Martin discovered the way, the box. Maybe he built the box. So this is something new. We can write a paper because of this. Or maybe something is happening near here. For example, in RFX lab in Padua. Or maybe something is happening now that is also interesting. Or we, or many people, are involved. Or there's a conflict about this. So people saying that carton box is better than a bottle, and they are facing somewhere in a very tough way. Or a present effect is really easy to explain, something that is, that is important for us now, or will be in the future. If you don't have any of this, you are not going to write a paper.
Yeah, if I can just step in for a second, it's interesting because I bring, it's a sort of personal experience. The first two, probably, parts are the starting point of our connection, because actually I met her because of a result that indeed we published, something like 2 or 3 years ago. We published, we got a pretty big result in Padua, and we get the cover page of Nature Physics, which is, Nature Physics is a big journal for physics, and there's something rather unusual. Now, first of all, it's unusual to get published in this journal. It's even more unusual to get the cover page. It was a nice experimental result, and these things, these kind of things, got the attention of the press. Because it was an Italian result, it went on a big paper, and of course it's interesting because she interviewed me, And eventually all of these end up, I was talking like today, and all went into, she explained me that 20 lines would have been more than enough for explaining these kind of things. But is the way we as scientists need to get trained to, because we have to cope with this. I can ask her I can tell you and her or her colleagues, thousands of nice stories about what we do in Padua, but nobody really cares. So this kind of, being able as scientists or as professional to cope with this, it's something that I'm learning myself. So this was just a small piece of personal experience.
Sensationalism is something we really look for. That's why energy communication is very often related to something dangerous. So we very often write or speak about energy when something dangerous happens. For example, this is the mushroom cloud that comes after an atomic experiment. Now you can't do this anymore. But this is, I think, one of the more known images in all over the world. And if you think about nuclear, this is one of the first thing you think about. And this is not my choice. This is how our head, our memory works. If you Google nuclear, this is what you can find. But nuclear is not, only this. Professor Martin explained, for example, that nuclear is fission. This is nuclear fission. But it's also fusion. And fusion is very, very clean kind of energy. No radiation, no pollution, no way to have these disasters, to kill people, and the only problem is we are not able to do it now. But so is nuclear dangerous? It seems, if you Google it, it's what you feel. But maybe it's not. If you have a look at this, this graphic shows the correlation between death from air pollution and accidents and CO2 emissions. And it shows that nuclear is near zero. That means that really more or less no death and no emissions for nuclear. Have a look at lignite. How does it? What's the right pronunciation? Lignite? Lignite, coal, oil. You see, oil is halfway. Coal is really worse. It's even radioactive. Something that we don't think about very often. But I don't know how many of you knows that coal plants are radioactive. Yes, they are. And they usually are more than nuclear plants. So this is how communication works, because nuclear accidents are really big, and they shock our imagination, they shock our view.
If I can just give a short comment on this, because we forgot to put the source. This comes from Lancet, which is made by doctors. So Lancet is one of the most highly reputed journals in medicine. So just to say, it's not done by physicists, by nuclear physicists.
And what is the time frame? In how long?
Oh, this one, I think this was, this is per terawatt hours actually. So yeah. It's by, you integrate into usage. You can read it into usage. Basically, it's telling you that there is a connection between the emission, the effect on the environment, and the casualties or the illness. That by the way, if somebody is interested, we can give it to you. It's a very interesting paper. It's pretty long, and it's analyzing all the effect on the public health of electricity production in the how to say, developed world and in the third world. It's very, very interesting from this point of view.
Okay. So who knows anything about NIMBY?
It's not in my backyard.
Yeah, great. NIMBY means not in my backyard. And what is this about? I mean, what don't you want in your backyard?
It means like that there may be some issues, like for example nuclear energy, and maybe just one example because I don't know how to explain. The government decides they want to build plants, nuclear plants, and like we just decide, okay, let's do that, but not here because here is dangerous.
Perfect. So it's not really the feeling that more or less everybody feels when someone proposes to build something dangerous or something that is perceived as being dangerous. You say, okay, yeah, we have to do it, but not near my house, not in my region, not my country, far away from here. And it's really a lot related to electricity. In 2011, in Italy, we had 163 new cases of people, saying, no, I don't want this kind of plant near my house. For example, many are related to renewables. You can see 88%. Many are related to mobility. For example, the TAV, the fast train in north of Italy. And 62% are electricity related. That means that producing energy is really difficult because you don't really know where to build new plants. Because nobody wants a coal plant near his house. And the question I will leave you with is, can energy be nice? This is a really, it's not only a fun subject, it's really a really important subject. Because what about if the plant they have to build was nice? Maybe, some nuclear plant or some eolic, wind farm, or some solar plant. What about if they were nice? This question has been asked to many architects all over the world, and these are the result of an international competition that is called LAGI. If you want to have a look, they had a 2013 edition. And these are, the last winner. This is all solar panels. And what about if the solar plant was like this? Would you like to have something like this near your house? Maybe, lighting in the night or something nice like this. Could this solve, the problem? This is just another way to communicate energy, another way to talk about this, another way to keep it, near to people. And thank you very much for your time.